I'm Dan from Playtika, and the group manager of the AI marketing. So Playtika is a huge company. It's actually one of the largest online gaming company in the industry. So in Playtika we have also a large AI lab with actually around 100 data scientists, MLEs, and data experts. So it's a huge lab in the industry. So the outline of this talk, so I'll introduce the waterfall auction and give some relevant background. And then I will introduce the graph revenue optimized waterfall strategy, or the growth in short. Then I will present some experimental result and summarize the talk. And you can ask me any question during the talk. Okay, so the worldwide spending in the digital advertising is huge. It's expected to increase the 600 billion this year. Most online companies are struggling to maximize revenue from such advertisement, and currently it's usually done in most company manually by a human expert, which is of course not optimal and not scalable. In Playtika we have a dozen of media buyers that are responsible only for this digital advertisement. Playtika actually has two hats. We also have the hat of a publisher and of advertiser. The new waterfall, we'll optimize it, and this cycle will continue. And we actually, I think it's the first time that someone published a real A/B test in a real business environment, and we demonstrated an improvement of 10% uplift compared to the industry best practice. Okay, so whenever users surf on a website or utilize mobile app, an advertisement real estate, which is called an ad slot, is allocated. So the allocated on an advertisement is usually referred to as an impression. The specific shown advertisement is selected in an online auction, which could be an online or a real-time bidding or any other type of auction. We'll talk about the waterfall auction, of course. So we have three key participants in this process. So we have the publisher, which is the consumer. We have the agency, which is the advertiser. And in the middle, we have the ad network like Google, Facebook, Unity, and all these giant companies. And in this talk, I will focus on the publisher side. As I said, Playtika has two hats, but in this time I will talk about the publisher side, which means that we have user and we want to, let's say, sell the user to a third-party advertiser. So the user can see advertisement within the app of Playtika. So a waterfall is one method to sell online advertisement via a network platform, and this is the topic of this talk.
Only
yes.
ad networks, or also
Sorry?
exchanges use only ad networks? Or
Yes, only ad networks.
exchanges like RTV or...
No, only ad networks. At least in the waterfall domain. So what is a waterfall auction or waterfall strategy? So it's composed of instances. This is rows in the table. Each belong to a specific ad network for a given price. For example, ad network of Google's, and the price could be $100 for 1,000 impressions, so it's 10 cents for a user. The ad slot opportunity will go through the waterfall from top to bottom until certain ad network decides to purchase the slot or to purchase the user. It's equivalent. So for example, the user or the slot will be offered first to Google for $100. If they refuse to buy the slot for $100, it will be offered to Facebook for $90. If they refuse, it will be offered to Unity until, as I said, someone decide to buy the slot and get the opportunity to present advertisement to the user. This is, of course, an online auction, so it has to take like a millisecond, so it's very, very fast. The publisher, which is in this case Playtika, controls the order and the prices in the waterfall, so we need to decide on the strategy. which means to set the order of the network, and they are called sequentially, as I said, and the prices of each instance. So the challenge is how to set it correctly or optimally in this case. So I will calculate the revenue of Waterfall. So again, this is an example of Waterfall with 6 instances. So actually the revenue is the summation over the multiplication of the price and the number of impressions. So for example, it will be $90 multiplied by the 2,000 impression, and we sum it up like for $10,000 revenue of this Waterfall. So W is the waterfall, I is the index of the instance in the waterfall, R is the waterfall length, the number of instances, QI is the price of the instance, and UI is the number of impression of that specific instance. It's counted for 24 hours. And so this is as I said, the revenue, the summation of the multiplication. The publisher maximizes the Waterfall revenue by controlling the instances order and the prices. Any change in the Waterfall influence all the columns of the impressions. For example, if Facebook will increase the price of this instance, so of course the number of impressions will decrease because Facebook will buy less slots for this, and as a result, the Unity number of impression will increase, because if they buy less, then more slot opportunity will come to Unity. But down the road of the Waterfall, we cannot know how exactly it would influence the other number of impression per instance. But any change will modify this vector of impression, and therefore the total revenue would also be changed. Ideally, we want to try all possible waterfalls and select the one leading to the highest revenue, but unfortunately this is not feasible because the number of possible waterfalls is exponential with the length of the waterfall, so we need to come up with something else.
And also,
yes?
Also the impressions is unknown when you calculate it.
So let's say that we know the total number of impressions, it's more or less the same every day. And we can normalize actually the revenue and calculate the revenue per user, so we can actually deal with it. So this is not a big issue. The issue is that I do some change, and all the revenue mix.
Are prices
yes.
calculated beforehand?
I need to set the price. It's not calculated. I need to define it. I can put it like 82. I can put it 84. You need to do it. So currently it's done manually. So like trial and error. I'll talk about it in a second. But we need to learn the prices, the right prices. So this is the slide. How it's currently managed. So usually it's managed manually by marketeers. So they will trial and error all kind of local changes. So for example, one day they can reduce the price of Facebook and see what will happen to the total revenue, and the next day they can try to switch between Unity and Vanguard and see again how it helps. But of course, this is not that good. It's not scalable. Just in Playtika, we have like hundreds of waterfall. Usually it's per country and OS, so as I said, it's really not scalable. And of course, it's not optimal. Yes.
Do you do the trial and error once a day?
Usually like every 3 days. This is the requirement of the ad network because they also apply a learning algorithm from their side, so they can force you not to do any change like with at least once 3 days or 7 days, depending on the network. Sorry, so where do we fit? So we propose, as I said, in this talk we'll focus on the waterfall optimization within this cycle, the one that will generate the recommendation of prices and order, how to do local changes in the current waterfall. And for that, we introduce the graph revenue optimized waterfall strategy, or in short, the growth. So first of all, we formalized the problem of waterfall optimization as a trellis graph, and then we can solve it with a Viterbi-like algorithm, which I will now describe. So this is an example of a trellis. So of course that this trellis graph actually compactly represents all possible waterfall. And here we describe the trellis graph. So what we can see here is like we have L layers. So L is actually an upper bound of R, of the length of the waterfall. And the number of, the size of L is actually the summation of all CI, which is the number of actually the maximum capacity that each ad network allows you to have. So you cannot have like 20 instances of Google. They also restrict it to have like 3 or 4 instances. Otherwise, you will have a waterfall of 100, 99, 98, 97 in trial option, and they want to increase their revenue, so they restrict us. And we have n nodes. So the nodes are all the combination of prices and discrete prices in an ad network. So this is the number of nodes in each layer. And as I said, the number of each layer is the number of combination of price and ad network. So each layer in the trellis graph represents all possible ad network instances coupled. So for example, if we have some path in this trellis graph, it will be a waterfall. So for example, the first instance can be like a Facebook 98, and then we can have another instance. The second instance will be Google for 85, and then we can have another instance of Facebook or Unity or whatever. So we need to actually find the optimal path, but this, as I said, compactly represent all possible waterfalls. Yes?
Yeah, is it monotonically decreasing over in the context of one provider?
The price decreases.
For Facebook, the layer number 2 can be higher than layer number 1.
So yes, the price in the waterfall has to decrease. Of course, it doesn't make sense to offer Facebook some user for like $80, and if they refuse it, to later on in the waterfall to propose it for $90. They refuse it for 80, they won't buy it for 90. So the price must decrease in the waterfall. Yes. Okay. So as I said, so this is the J layer, and the relationship between any pair of nodes from 2 consecutive layers is actually can take the value 1 or 0. So 1 is that an edge exists between 2 nodes of 2 consecutive layers. Note that if it's 1, it doesn't mean that the edge is in the optimal path, but it means that it's a valid one. And 0 if the path is not valid. So we'll talk in a minute about some constraints. So for example, I cannot have 2 instances of Facebook, and I cannot have 2 instances of Facebook for the same price. So for example, this edge here is not feasible, and so this is how we represent the edges. And as I said, each node is a potential instance in the waterfall, and the edges impose the constraints. So a very important property of Viterbi actually is the dependency separation. So actually every layer separates the next layer and the one that precedes it. So for example, in this case, this layer, the J minus 1, separates the J layer from the J minus 2. This is an important property of Viterbi. And actually it means that each node, for example, the 9th node in the J layer, it has only one node that leads to the highest revenue for this node. So it has one optimal path that leading to it. So it will have one node in the previous layer that will be the parent, the best parent node of this node, and therefore it will be disseparated or undependent in any of this layer. Talk in a minute about the forward and backward passes.
What's the D?
this dependency separation.
It's not a parameter.
No,
Okay.
it's a shortcut. It's a common shortcut for dependency separation. So they are independent given the intermediate layer. So the node 9 depends in all the nodes in this layer, but not on the nodes from the J-2 layer. So actually the goal of the algorithm is to find the green path, which will be the optimal path or the path leading to the highest total revenue. And we have a forward path and a backward path. So in the forward path, the growth utilizes the D-separation to find the best parent of each node. So for example, the best parent, we start actually from the left. So the best parent of node 9 will be node 2 of Facebook, and the best parent of this node can be any one of this layer nodes. So this is the forward path. And in the backward path, we actually just need to do a trace back for the optimal path. We have the best, the node with the highest revenue, and we see who is his best parent. This is his best parent, and who is the node 3 best parent to be this one, and we can trace back and get the optimal path. And now, before I will talk about how we calculate the revenue, just a few words about the constraints, which I mentioned earlier. So the constraints determine which paths are valid. We call it the edges, if they are 0 or 1. We distinguish between local and global constraints. Local defines the edges, while the global influence the paths. And we also distinguish between active and inactive, or actually not known, it's inactive paths. Sorry. So the local constraint, they does not influence the D-separation property of the algorithm. So and we'll give two examples of local constraint. So the first one is that two consecutive instances cannot belong to the same ad network. So for example, I talked about it a few minutes ago. What would happen if they give up? What would happen in this case? Then Facebook will probably do their own test, and they will randomly give up 10 random users for $82. And surprise, surprise, they will see that all the 10 users, the random selected 10 users, will be in a few seconds later will be offered for $66, so they can induce that there is no instances between them, and then they will never buy any user for 82. They will always buy for 66. So this is why we must have some other ad network in between. So this is one example of local constraint. Another one is the prices. So the prices of the waterfall are ordered according to the price. As I said, if Facebook refused to buy someone for $82, there is no reason to propose the same user for 85. There is no chance they will buy it. You just waste. It's a waste of instances. As I said, we have a restricted number of allowed instances per ad network. And the global constraint. So the global constraint, on the other hand, they might violate the D-separation property of the Viterbi solution, which will lead to a suboptimal solution. For example, the network restricts the number of allowed instances in any waterfall, usually 4, 5, or 6, depending on the network. And inactive global constraints. So the definition is that if the growth solution for the waterfall strategy does not violate a global constraint, even so it was learned while ignoring the constraint, we call the constraint an inactive global constraint, and vice versa the non-active. So what is the output of the recommendation? So as I said, it's a list of recommendations of local changes within the waterfall. So the media buyer chooses what to adopt and what not. And consequently, the new data or feedback is collected. We have a new waterfall. We optimize it, generate new recommendation, and the cycle repeats itself. So as I said, we need to, every time I talked about the trade graph, I talked about revenue, but I didn't mention how we calculate this revenue. for every node, of course. So we need to estimate theta of the ad network and the price. So of course it's very hard to calculate this integral, and we want to utilize the historical data. So we'll actually use a summation instead of the integral, which is approximation result. So for that we use the matrix M. So this is the summation instead of the integral. So what is this matrix M? So the row are prices and the columns are the ad networks, and each entry in the table is actually some function of past auctions. So similar one can be the average number of impression, or we can use some more sophisticated function there. And for example, the green line represent one possible waterfall. So for example, you can see a waterfall of the first instance is Google for 88, then Facebook for 86, and etc. So this is one waterfall. This is the graphical representation of this specific waterfall. And using this matrix, let's say we want to calculate the actual revenue of the fourth instance for $83. So for Facebook, $83, it will be $83 divided by 1,000, because we have, as I said, the prices are per 10,000 impressions. And we multiply it by the summation of 447, 120, and 12. We stop here because there is another instance of Facebook for 83. So all the users that are from here and above will be bought by this instance. So the revenue of this instance is just this calculation, very, very simple. So this is how we calculate for each node. We can calculate for each node in the waterfall its revenue. Question? Yes.
What is the input to the network? Your historical data?
Yes, this is the input. This is
No, for the Trellis network.
so the trellis is just a graphical.
It's a model.
Yeah, it's a model.
You don't have data for this model because you have.
No, it's not like a neural. No. It's not like a. Yeah, it's not like a neural. It's not a network like a neural network. It's just a logical representation of how to do all the calculation of each node. So I want to calculate, for example, the revenue of this node. Then I do, as I said,
Then you have this flow.
Yeah. So for example, the revenue of this node is the revenue of the best parent from here with the revenue of this second instance. So we go from left to right, and I try to fill all the revenue of each node until I get to the last layer. Then I have the revenue of all this node, and I take the one with the highest revenue, and I go back, and I have the optimal solution. Yes?
Yeah, I have a question. So this waterfall auction is a sort of Holland auction, right? And the green price.
Yes.
Yes, and it's equal to the one price auction, cost price auction.
No, it's different. It's another type of auction. Very different.
Still verification. Why this approach works better than RTB, like a real-time bit?
So it's a good question. It's very good not for the publisher and not for the advertiser. This is the best solution for the ad network, for Google, Facebook, because they make the most money of it, and they decide. So this is why we have to use it. So actually the world is now turning to more real-time auction, and the waterfall now there are some hybrid models. It's another topic we can discuss. Okay, so some experiment. So first of all, we compared ourselves to other state-of-the-art solution. We compare four different waterfalls. So you can see here in the table only the improvements, and you can see, of course, that the growth is much better than all other algorithms. Next, we conducted an A/B test. So it was a real-world waterfall. We split the waterfall to two. So one was managed manually by a consortium of several experts, and the other by the AI model. The user were randomly split between the waterfall based on the fifth digit of the device ID, and once a week the human expert and the AI modified their corresponding waterfall independently, but at the same time. We conducted a 6th iteration, and this is the result. So we can see that the green one, the AI-based model, was actually better during the entire experiments in all the iteration. The difference was statistically significant according to a Wilcoxon sine wave test, and it showed a huge increasement in revenue to Playtika. And to summarize, the settings were discrete prices, multiple instances per ad network. We formalized the waterfall auction problem as a trellis graph and solved it with a Viterbi-based algorithm. And we conducted an A/B test to validate the method superiority. Finally, future research should concentrate on combining waterfall optimization in real-time bidding, as you mentioned, like hybrid auctions, to use non-discrete prices, and to consider the Viterbi as a target function of a waterfall reinforcement learning framework. And if someone is interested, the code and the data and the paper and everything is publicly available. And that's it. If you have any question. Yeah, sure.
One more question. So maybe I missed something, but you never said about the context. It's quite clear that for different users, different games, different context, you have a different price.
Mm-hmm. Yes. We have a what?
From the demand side, they also can decide if they'd like to buy this or not.
Right.
So and you can actually predict the price for different contexts, right, from your side.
I don't have I can have a context of the user. Yeah, I can do some prediction.
Because if you send a request for them, you send some kind of features, and they decide the price if they want to buy this or not. But you can actually have the same features to predict the price.
Right, but I don't know in advance which user will ask to see an ad. Right. I don't know it in advance. So the user start playing.
Publisher get this event first, right? So you have the first.
I'm the publisher.
Yeah.
Yes.
So you have this event on your side, so you have this opportunity to show the impression to this user and know everything about the content, right? You send the request to different media buyers if they want to buy it.
To ad networks, yeah.
If you have this context, you have a country.
But the waterfall is predefined. I cannot have a waterfall per user or decide on different prices per user. This is because Google and Facebook want to maximize the revenue. No, but it's not up to me. The waterfall is like an agreement between me and Facebook, between me and Google. We have a signed agreement, and we need to set it once. As I said, like every 3 days, I can do a modification in the waterfall. But again, it will be global to all users. I cannot do it user.
An average price for any context.
Yeah, exactly.
Maybe a related question. Since you are aiming to the mean, to the average, it's a side question. Can they attack you by giving you like a anomaly, like
So actually,
your mean?
Yes, so this is why it's an ongoing process. Of course, they apply a learning algorithm from their side to maximize their revenue. So it's a contest.
Learning. They can bias your.
Yeah, it's a contest. So this is why we need to keep training the model. It's a big context. Okay, thank you.